Hi guys, so we are going to record neutralization reaction so that everybody can watch it at home. So we are here live with some portion of your class. So neutralization reactions are a special kind of double replacement reaction. We know that in a double replacement reaction, we always have a binary compound. Binary means that there's two parts. So we'll have the positive ions and the negative ions swap their partners. In a neutralization, an acid and a base, we know that acids give off hydrogen ions as their only positive ions, and bases give off hydroxide ions as their only negative ions in solution. So we know that the positive ion H+, the negative ion OH- are always going to bond with each other to form water. So let's identify which of these substances are acids, bases, salts, and water in the following reactions. So the first reaction is sodium hydroxide reacts with hydrochloric acid to yield water and sodium chloride. So NaOH, I'm just going to ask you guys in a row here, all right? So NaOH, acid or base? Base, absolutely. HCl, acid or base? Acid, very good. H2O is? Water. Sodium chloride is a salt. Very good. So we know that a base and an acid or an acid and a base, because these are colliding with each other, the plus sign means that they're hitting into each other. It's communicative. It doesn't matter the order. What does matter is what's on the left side of the yield and what's on the right side of the yield. All right, so let's do the next one. All right. So H2SO4 is an
acid.
Acid, absolutely. We know that because it starts with a hydrogen ion. You'll notice that it gives off two hydrogen ions for every one H2SO4, so we call that polyprotic or diprotic. It gives off two protons for every mole of acid. All right. CaOH2 is a base, absolutely. So it doesn't matter if you have the base first, and the acid first, or the acid and then the base. All right. Back over here. Calcium sulfate is a salt. That's the salt. Very good. And H2O is water. So, simple enough. It's always going to be an acid or base. It's always going to make a salt-water solution. That salt-water solution will always have a pH of 7 because it will have an equal amount of hydrogen ions and hydroxide ions. All right, so let's try the next two. So for number 3, I have the reactants, and same thing for number 4. So on your own, try and number 3 and number 4. Number 3 is HNO3 plus KOH, and number 4 is CaOH2 plus H3PO4. So if you're watching at home, pause the video. All right, and we're back. So in the first reaction here, you're going to want to dissociate the ions. So I like to do a work line. I'm always going to dissociate my ions. HNO3 is going to be an acid. It's going to form hydrogen ions as the only positive ion in solution. And it's also going to form nitrate ions, NO3 minus. KOH, what's it going to dissociate into? Go ahead.
K plus and OH minus.
Yep, K plus and OH minus. So when we do the products here, the positive ions I like to keep in the same order and swap the negative ions. It's just my convention. So I'm going to go ahead and keep my H plus, and I'm going to bond it with my OH minus. What is this product going to be?
H2O.
H2O, or you can write it as HOH. Both are completely acceptable. I'm actually going to write it as HOH. Because lots of times for balancing purpose, it actually makes it easier to think about how many hydrogens and how many hydroxides you have instead of making it into H2O. But you can write it either way. They're both correct. What will the other product of this reaction be? It's going to be K plus, and that's going to bond to NO3 minus. All right, so that's right, KNO3, which is our salt, potassium nitrate. So we end up with an acid, a base, a water, and salt. All right, so next one In this example, we know that there's more than one hydroxide given off by the base, and there's more than one proton given off by the acid. So we're going to need to balance once we finish this. So the ions here are Ca2 plus and OH minus and H plus and PO4 3 minus. All right, so we know that I'm going to keep the positive ions in the same order, and I'm going to swap out my negative ions here. So I end up with Ca is 2 plus, phosphate is 3 minus. So what's the formula going to be for the calcium phosphate? Ca3PO4 exactly. Don't forget that you need parentheses when you multiply the polyatomic. And then my other product here is going to be my H plus and my OH minus. And we know that H plus and OH minus make water. And we can write that as HOH. Now, when we go to balance this reaction, where do I need a coefficient? Which element is out of balance right now? Go ahead.
The calcium.
Yeah.
A 3 in the beginning, a 3 coefficient beginning.
That's exactly right. The calcium, we have 1 calcium on the left side of the reaction, but we have 3 on the right side. So we're going to multiply calcium hydroxide by 3. Now, how many hydroxide ions do we have now on the left side of the reaction? 6. So, the reason that I like to write HOH is because I like to keep my hydroxides as that hydroxide polyatomic. It makes it easier for balancing. I know I'm going to need 6 of them, so I'm going to add a 6 coefficient here. Now I know that I have 6 hydrogen ions. So I'm going to go back and make 6 hydrogen ions on the other side. So what coefficient should I have for phosphoric acid? 2, exactly. And does that work out for our phosphates? Sure does. So we know that it's 3, 2, 1, 6 in our balancing. All right? All right, so now that we know that neutralization reactions are an acid and a base reacting to form a salt and water, we can use this quantitatively. So we've been talking qualitatively, but now we can quantify this. We know that the same number of hydroxides and hydrogen ions need to react with each other in order to end up at neutral. You need to have 6 hydroxides on the left side and 6 hydroxides on the right side, 6 hydrogen ions on the left side, and 6 hydrogen ions on the right side in this example to make it exactly neutral. If you have extra hydrogen ions, it'll be an acidic pH. If you have extra hydroxide ions, it would be a basic pH. If you have the exact same amount, that is neutral. So we can do this quantitatively using concentration. So can you take out your reference tables and turn to table T, find the formula for concentration in terms of molarity. All right, so molarity is equal to, go ahead. That's right, moles over liters. So molarity is a little weird in that we write moles over liters, which is mixing together units with the factor. So we're going to rewrite it that molarity is equal to the moles divided by the volume. All right, so molarity, you can also write it is equal to the moles divided by volume. Just turning that liters into the unit. So if I cross-multiply this equation, which we did when we did solutions, you get that the molarity times the volume is equal to the number of moles of that substance. Right? So we're just cross-multiplying our molarity equation in order to get that the molarity times the volume is going to give us the number of moles of solute. Now, since we know that in a neutralization reaction, the moles of acid are equal to the moles of base, we can use a system of equations to rearrange this and say that since the moles of acid are equal to the moles of base, we can also say that the molarity of the acid times the volume of the acid is going to be equal to the molarity of the base times the volume of the base when neutralization occurs. This is useful because we can use it to determine the concentration of an unknown acid if we have a base we know the concentration of, or an unknown base if we have an acid we know the concentration of. And we react them together, and when they get to neutral, we know that they're equal to each other. So, on your reference tables, find the equation that says titration. It's on table T. You should already be looking at table T. So, Ma, you'll notice, does not actually stand for molarity of the acid, but instead, Ma stands for the concentration of which ion? H plus, the hydrogen ion, absolutely. Now this is important because when you have an acid like H2SO4 that gives off 2 hydrogen ions for every 1 mole of acid, you're going to need to take that into account because you need to determine the concentration of hydrogen ions, not the concentration of the acid. If it gives off 2 hydrogen ions, it's going to be twice as much. If it gives off 3 hydrogen ions, it's going to be 3 times as much. The Va stands for volume of acid. Mb, just like Ma, doesn't stand for the molarity of the base, but instead that ion. So Mb is going to stand for the molarity of the hydroxide ion. NVB is going to be the volume. All right, so let's do some practice problems. You're going to need your calculator, so you can take those out. All right, so here are 2 Regents examples of titration questions. The first one is a student neutralized 16.4 milliliters of hydrochloric acid by adding 12.7 milliliters of 0.620 molar potassium hydroxide. What is the molarity of the HCl acid? So if you're watching at home, pause the video and solve this problem. All right, so I'd like to highlight all of the acid in one color. So this would be 16.4 milliliters of HCl. And I'm going to use a different color in order to talk about the base. Potassium hydroxide is the base, so I'm going to highlight my 12.7 milliliters here and my 0.62 molar here. And that tells me that my 2 base values will always be multiplied by each other, and the acid will be the one with the variable next to it. All right, so here is the setup. I have highlighted the acid in yellow and the base numbers in green. And you can see that I plugged in here. The molarity of the acid is our unknown. And when you multiply and then isolate your variable by dividing, you should end up with answer choice 2, which is 0.480 molar. All right, go ahead and try this next question. The answer choice is, oh, it's not a multiple choice, my bad. All right, so you should have gotten 0.1926. Since we're rounding to 3 sig figs, it would end up being 0.1.